The other thing the Verticopter features to help during vertical flight is an artificial stabilization system. This is basically a set of sensors that tell an onboard computer the position of the plane and relay a set of commands to the control surfaces and puffers to maintain stability in the case of zero pilot input, or to safely execute the pilot's desired commands without losing control. Since the manned versions of this plane are conceptualized with a fly-by-wire control system, it basically means that the pilot's inputs are sent to a computer first, which also receives inputs from the sensors. The computer then determines the best course of action for the plane to take, given its attitude and the pilot's input. This also applies to the drone and the remote-controlled planes, although it only affects the pitch axis. This reflects the scenario where a radio-controlled plane is equipped with a gyro, which would help the pilot maintain pitch stability during the transition from vertical to horizontal flight and back. This system is, in fact, in place for Garo Aircraft's actual RC prototype. The manned Verticopter's artificial stability system is set up in such a way that it'll bring the plane back to level flight if the pilot lets go of the controls. It will also limit the maximum amount the plane is allowed to pitch and roll to 35 degrees during hover. So, if you fully deflect the controls to the left, the computer will tell the ailerons and puffers to tip the plane left until it hits the 35-degree mark, at which point they will deflect back to zero, and the computer will do whatever it needs to do in order to maintain that angle until you move the controls back. This system will gradually start phasing out the more forward speed the plane picks up. At full forward flight, the artificial stability system is completely disengaged, and the pilot inputs make it directly to the control surfaces 100% of the time in the manned scale sizes. The unmanned versions retain the artificial stabilization system about the pitch axis throughout their entire speed envelope. Like the puffer system, the artificial stability system can be disengaged, allowing the pilot to get a feel for the natural behavior of this plane. It is quite docile, and unaided vertical flight can be mastered even with no prior VTOL or helicopter experience. What makes hovering a challenge is the fact that the forces acting on the plane are not ironed out by inertia or air resistance, as it would during regular forward flight. Also, instead of just following its nose, the plane needs to be kept under control in all flight directions, be it up, down, sideways, forward, or backward. One thing that is particularly noticeable is the inertia the plane has about its rotational axes during hover. If you give some yaw or rudder input, the plane will continue to pick up rotational speed as long as the yaw input is given. So, to settle the nose into a given direction, yaw commands have to be given in moderation and enough space left for a counter yaw measure once the desired direction has almost been reached. To perform a hover with the artificial stabilization system disengaged, constant corrections need to be made by the pilot. The tendency is to overcompensate. If the plane banks left, the natural response is to give it right stick input until it is level again. But once it's level, the inertia will actually keep rolling the plane towards the right, and a counter input will usually result in ever-worsening oscillations and an eventual loss of control. To avoid this, it is crucial to act in anticipation of inertia. If the plane makes an undesired motion, try countering it with small movements, anticipating the point at which the rolling motion needs to come to a halt, and giving slight counter roll just before settling into the desired angle. This can be learned intrinsically, much like maintaining balance on a bicycle is attained through practice more than through theory. However, understanding the underlying phenomena may speed up the acquisition of the feel required during hover. Fortunately, the artificial stability system, like training wheels on a bike, takes this load off the mind of the pilot until he or she is ready to tackle unassisted hover. During forward flight, the Verticopter is capable of very high speeds and is very maneuverable, although it retains quite docile flight characteristics. It's equipped with a fully functional autopilot, which is documented in the flight manual included with the Verticopter. Aerobatics are extremely fun with the Verticopter, and its swiveling thrust vector allows for a lot more creativity during aerobatic routines, as well as precision flying. Landing the Verticopter has been the focus of a number of improvements over the older versions of this plane. One major improvement has been the elimination of a pitch oscillation during transitioning from vertical to horizontal flight and back. Swiveling the prop assembly during full speed now barely has an effect on pitch. The time it affects the pitch of the plane is if the airstream generated by the props, also called prop wash, hits the horizontal stabilizer at an angle. Between 15 and 25 degrees of vector angle, the prop wash gets bent by the horizontal stabilizer, causing a nose-up moment. This phenomenon is obviously a lot more pronounced at higher throttle settings. So, if the thrust vector is altered during high-speed forward flight, it is advisable to throttle down a bit before proceeding. Another major improvement was the addition of speed brakes. Normally, an airplane's speed brakes deploy as spoilers on the top of the wings, also helping press down the plane's wheels during landing, increasing the traction needed for braking. But for the Verticopter, a plane that normally does not require a landing strip, it was more important to maintain a neutral pitch moment during the deployment of the speed brakes. Another important consideration for this design was also trying to avoid added weight and complexity. Since the Verticopter already has an onboard computer, it was decided using existing control surfaces as speed brakes would be the way to go. So when the pilot deploys the speed brakes, the outer elevons deflect downward, while the inner elevons deflect upward, causing the drag needed to slow the plane down without adding complexity, weight, or pitch moment. This addition alone can help slow the plane down from its top speed to the point of vertical touchdown in less than 30 seconds. Thanks to these updates, pinpoint landings from high-speed approaches are very possible and can be an exciting challenge for Verticopter pilots. Thanks to the Verticopter's resilient landing gear with extra long travel and custom damping constants, it is a very forgiving plane to land. Even in the event of dual engine failures at low altitude, the phenomenal glide ratio the large wings provide and the tremendously absorbent gear struts will take the abuse with stride. The 7-seater, formerly equipped with shorter landing gear, has been upgraded to full-length landing gear, allowing for complete prop clearance when vectored fully forward. This required the addition of retractable ladders in the cabin doors, which can be opened and closed with a pre-assigned key or joystick button, or with a canopy slider in the cabin. The paint schemes of the Verticopter can easily be changed, and now all planes can make use of paint schemes that were released in version 1.3 of the 2-seater. The radio-controlled planes partially reveal their balsa and plywood construction and offer a glimpse into the planned real-world radio-controlled kits which are currently being developed. A number of paint schemes are available for download from Verticopter.com, and included in the Verticopter download is a tutorial that helps you easily create amazing paint schemes of your own. The Verticopter's technology is patented and unique in the world of VTOL technologies, and Garo Aircraft is taking a tiered approach to making this plane a reality. This approach makes use of all the lessons that can be gleaned from both the virtual world and the world of radio control, moving to more serious applications such as UAVs and drones for surveillance, border patrol, and military use, and ultimately tackling the challenges of the manned tier of this design. It is with great pleasure that I offer this plane to the public as a virtual, flyable, high-quality aircraft compatible with Windows, Mac, and Linux machines. Visit Verticopter.com for more information, or check out my YouTube channel to see more of the Verticopter in flight.